You live in a universe held together by a particle no one has ever caught on its own, not once, and yet it is responsible for almost all the mass in your body. But before we continue, please subscribe to the channel to give your support. Let's continue. You already know its quieter cousin, the photon. Photons carry the electromagnetic force. They are why light exists, why radio and Wi-Fi work, why atoms can interact across space. A photon can travel from the Sun to Earth, about 150 million kilometers, roughly 93 million miles, and it stays a clean, detectable quantum all the way. We build cameras, telescopes, phone sensors, all based on grabbing photons. The gluon is a strong force carrier, and it works in a completely different regime. Instead of linking atoms across meters or miles, gluons glue quarks together inside protons and neutrons. A proton is tiny, about 0.84 femtometers across. A femtometer is 1/millionth of a billionth of a millimeter. You could fit more than a billion protons in a line just to cover 1 meter, a bit over 3 feet. Inside that tiny volume, the strong force is so intense that trying to separate the quarks takes more energy than launching a rocket into orbit. Think about ordinary technology for a second. To put a spacecraft into low Earth orbit, you need speeds around 7.5 kilometers per second, about 17,000 miles per hour. That corresponds to a huge amount of energy per kilogram of spacecraft. Now compare that to the energy stored in the strong interaction inside a single proton. When you try to pull its quarks apart, you very quickly reach similar energy scales, but concentrated into distances about 10 trillion times smaller than a millimeter. That is the scale at which gluons operate, all the time, everywhere in normal matter. So the natural question is, how strong is this strong force, really, compared with the forces you're used to hearing about? Electromagnetism already looks powerful in daily life. Lightning can involve hundreds of millions of volts. Industrial machines and particle accelerators use electric fields strong enough to rip electrons off atoms. Magnetic resonance scanners use fields tens of thousands of times stronger than Earth's magnetic field. At human scales, that feels like maximum power. But go down to distances of about 1 femtometer. That is a millionth of a billionth of a millimeter. And the numbers change. At that range, the strong interaction between quarks is not just a bit stronger than electromagnetism, it is tens of times stronger. The force does not fall off quickly with distance. Instead, it behaves almost like a string with a constant tension. Physicists describe that tension as about 1 giga-electron volt of energy per femtometer of length. In plain language, if you could somehow stretch the connection between two quarks by 1 femtometer, you would store an amount of energy similar to the mass energy of a proton itself, but concentrated into a distance completely beyond ordinary experience. If you tried to scale that up to a centimeter, less than half an inch, the energy would be absurdly large, far beyond anything we can generate with current technology. So, at its natural scale, the strong force is the dominant interaction. Gravity is irrelevant there. Electromagnetism is secondary. The weak force is a small correction. The gluon's force is the one that decides whether atomic nuclei exist at all. Without it, atoms would fall apart, stars could not form, and chemistry would not happen. Given that it's this important, you might expect that we would have direct pictures of gluons the way we have tracks of electrons or flashes of photons. But that leads to the next strange fact. Why have you never seen a single isolated gluon? There's no handheld gluon camera. There's no detector that records a gluon hit flying freely through a lab. We catch photons in simple devices like solar cells. We see muons and electrons leaving clear tracks in bubble chambers and modern detectors. Even neutrinos, which almost never interact, can be spotted by building massive tanks filled with water or ice and waiting for rare flashes. Gluons never show up that way. Every attempt to pull quarks apart far enough to expose the gluon field between them runs into the same barrier. As you separate the quarks, the strong force does not weaken the way electric forces do. The energy in that color string between quarks increases with distance. Very quickly, the energy stored in the gluon field is high enough to create new particles. At that point, the system does something radical. Instead of giving you one quark moving off on its own, the energy turns into a new quark-antiquark pair. The original connection splits into two smaller confined systems. You end up with two composite particles, two hadrons, each color neutral, instead of a single exposed quark and a loose gluon. The gluon's energy is present, but it's locked inside these bound states, not flying free. This behavior is called confinement. It's not just a mathematical curiosity. It's an experimental fact. No one has ever detected a single free quark or a single free gluon. Whenever high-energy collisions try to create them, they transform into sprays of hadrons instead. The universe seems to enforce a rule. You never see the raw building blocks by themselves, only in combinations that hide their color charge. So you might suspect that the simple diagrams you see in textbooks are hiding something. Those drawings show quarks as little dots and gluons as curly lines between them. It looks neat, like a few simple connections in a network. Is that really what's happening? Those diagrams are useful shorthand, but they're extremely incomplete. In the full theory, the gluon field is not a thin line. It's a continuous field spread through space, and it has a key property that photons don't have. In electromagnetism, the photon doesn't carry electric charge. That means electromagnetic fields respond to charges and currents, but they don't directly create more charge themselves at the most basic level. Light beams can cross each other without interacting much. Gluons are different. They carry the same color charge that they respond to. This means gluon fields interact with themselves strongly. In the equations of quantum chromodynamics, there are basic interaction points where 3 gluons meet and others where 4 gluons interact directly. You don't have an equivalent simple vertex for 3 photons in basic quantum electrodynamics. Inside a proton, this inter-self interaction matters. You don't just have 3 quarks exchanging a few gluons like a balls in a game. You have a dense, constantly changing cloud of gluons creating more gluons, interacting with each other and generating short-lived quark-antiquark pairs. The field lines of the strong interaction don't spread out smoothly and fade with distance. They tend to bunch into narrow tubes between colored objects. That's why trying to pull quarks apart simply pumps more and more energy into the gluon field until new particles appear. This is the deeper reason the gluon isn't the nice messenger particle. It's not a separate calm carrier passing force from one place to another. It's part of the structure of the proton itself. The same field that glues quarks together is also responsible for most of the proton's mass and for the way it reacts in high-energy collisions. So you have a particle that never exists freely, that carries a force far stronger than anything you meet in daily life, and that interacts with itself so strongly that the usual simple pictures of fields and forces start to break down. That raises the next question. If the gluon carries this special color charge, and it comes in multiple types, what does that actually mean? And why are there 8 of them instead of a simpler number? Why does a strong force bother with this strange thing called color at all, when electric charge already exists? You've heard that quarks come in red, green, and blue. That sounds like a toy model, but it's actually a compact way to talk about a very specific kind of symmetry in the math, called SU3. You don't need the full math, just the idea. The strong force cares about this abstract color much more than it cares about ordinary electric charge. 2 particles can have the same electric charge, but if their color is different, the strong force treats them differently. Here's the basic picture. Each quark carries one color, red or green or blue. Each antiquark carries one anticolor, anti-red, anti-green, or anti-blue. The strong force tries to build combinations where all the color cancels to neutral. Like a proton has 3 quarks whose colors sum to neutral, like adding red, green, and blue light to get white. A meson, like a pion, is a quark and an antiquark, say red and anti-red, and that also cancels to neutral. The rule is simple. Anything that can exist freely on its own, anything that can fly through a detector as a complete particle, has to be colorless overall. This is why you never see a single quark by itself. A lone red quark would carry net color. The strong force field around it could not cancel out, so as he tried to pull it away from everything else, the energy in that field would just keep growing. Instead, quarks lock themselves into groups where the colors cancel, so the outside world only ever sees neutral objects like protons, neutrons, or pions. You never get a naked color charge. So where do gluons fit into this picture, and how many different kinds are there really? Your first guess might be one gluon for each way to swap colors. Maybe a red anti-green gluon that can turn a green quark into a red quark, a blue anti-red gluon that turns red into blue, and so on. If you list all possible combinations of one color and one anti-color, you get 9. That sounds like a clean answer. 9 gluons, done. But the SU3 symmetry does not allow all 9 to be independent. When you actually work through the math, you find that one particular combination of those 9 acts like a completely neutral object with respect to this color symmetry. It doesn't really participate in the strong force in the right way. That combination gets thrown out. The remaining 8 combinations are the true gluon states that carry color and actually mediate the strong interaction. This is not a naming trick. It comes straight from the way SU3 is built, from its structure constants in the equations. And this is not something physicists just decided to believe. They check it in data. In high-energy collisions, for example at CERN, quarks and gluons come flying out of the interaction point with energies of tens or hundreds of GeV, that is tens or hundreds of billions of electron volts. They don't hit the detector as quarks and gluons. Instead, each one turns into a spray of hadrons called a jet. The way those jets split, branch, and spread out depends on how many kinds of gluons exist and how strongly they interact. You can take a theory that has 9 gluons and one that has 8 and ask each one, what jet patterns do you predict? When you compare to real data from detectors, the 8-gluon theory matches the detailed distributions, the angles, the particle counts. The 9-gluon version does not. So the 8 is not just a pretty number tied to a fancy group name. It is baked into the behavior of real particles slamming into each other at close to the speed of light. That leads to the next step. If gluons are different from quarks, can you actually see a difference between jets that start from quarks and jets that start from gluons? At collider energies of hundreds of GeV, you routinely produce both kinds. Detectors don't label an individual jet with a tag that says, this one came from a gluon, but you can separate them statistically. When you group many jets and analyze them, a clear pattern appears. Gluon jets are on average wider and contain more particles than quark jets with the same total energy. The reason is the effective color charge each type carries. In the strong interaction, there's a number that tells you how strongly a particle radiates gluons. For quarks, that number is about 4/3. For gluons, that number is 3. 3 is bigger than 4/3, so a gluon radiates more gluons than a quark does, all else being equal. That extra radiation has a direct, concrete effect. Take jets with the same energy, say a few hundred GeV. On average, gluon jets produce about 1.5 times as many charged particles as quark jets with the same total energy. If a typical quark jet in that range has roughly 20 charged tracks in the detector, a typical gluon jet might show around 30. You also see that gluon jets spread their energy over a slightly larger angle. Experiments measure all these details and compare them to quantum chromodynamics calculations that include those specific color factors. The agreement is very good. This is how you count gluon behavior without ever seeing a single free gluon. You infer it from the way energy turns into hadrons, from how crowded and wide the jets are. The fact that the numbers line up only when you use the SU3 color factors and 8 gluons tells you that this abstract symmetry is describing something real, not just a blackboard game. Now connect this back to your basic picture of what a force carrier is supposed to be. Maybe you started with a simple idea. 2 particles have a charge and a boson moves between them, carrying the force, like a ball tossed back and forth. That works reasonably well for electromagnetism. Photons do not carry electric charge themselves, so they don't act as sources. They're neutral messengers. The strong force does not fit that pattern. In quantum chromodynamics, the carriers themselves, the gluons, also carry color charge. They're not neutral middlemen. They are part of the charge system. On top of that, there are multiple types of gluons tied together by the SU3 symmetry, and they can turn into each other, split, and merge. So the force is not two charges plus one messenger. It's a whole network where the messengers constantly interact, radiate, and multiply. And this already breaks the simple, just shuttling a boson back and forth force picture. If the thing that is supposed to carry the interaction is also a source for that interaction, and it comes in several types linked by a non-trivial symmetry, you never get a clean, isolated carrier. You get a dense cloud of activity that you can only describe with field theory and probabilities. And that brings up the next problem. If the gluons are this tangled and self-involved just from the symmetry side, what happens in real space when you actually try to pull two quarks apart and see how far the strong force will let you go before everything breaks? How far can you actually pull a quark before the universe steps in and says, no further? Start with one proton. It's about 0.84 femtometers across. A femtometer is 1/quadrillionth of a meter, a millionth of a billionth of a millimeter. That's far smaller than an atomic nucleus, which is already tiny compared to the whole atom. Inside that proton, you have three valence quarks, plus a sea of gluons and quark-antiquark pairs. Now, focus on just two of those quarks, and ask, what happens if you try to pull them apart? At extremely short distances, less than about 0.1 femtometers, the strong force between them actually gets weaker. This is the regime where the coupling is small. The quarks behave almost like free particles, and our usual calculation tricks work well. You can treat the interaction a bit like you treat electromagnetism, with corrections. This is part of what's called asymptotic freedom, and we'll go deeper into that later. But you don't live at 0.1 femtometers. As you pull the quarks farther apart, heading towards distances around 1 femtometer, the effective potential between them grows roughly in proportion to the distance. In simple terms, it starts to act like a string with a constant tension. That tension is about 1 billion electron volts of energy per femtometer. 1 billion electron volts is similar to the total rest energy of a proton. So stretching the color string between two quarks by just 1 femtometer stores an energy comparable to the mass energy of the entire proton, packed into that tiny additional gap. A few femtometers of extra separation, which is still smaller than the diameter of a typical atomic nucleus, is already enough energy to do something extreme. At that point, the system is more interested in creating new matter than in letting the string keep stretching. Quantum field theory allows energy to turn into particle-antiparticle pairs. Once that color string holds a few billion electron volts, the strong force does exactly that. It pulls a quark-antiquark pair out of the vacuum. That is not science fiction language. It's a standard process. Energy becomes mass, consistent with Einstein's relation between mass and energy. So what do you actually end up with? You don't get one quark drifting off alone with a clean gluon field stretching behind it. Instead, the color string effectively snaps, but not the way a mechanical rope breaks in two pieces. In the strong interaction, the energy stored in that stretched flux tube reappears as the mass and motion of the new particles. The color keeps hidden at every stage. Before the break, you have a single color-neutral object. During the stretch, the flux tube carries color, but it is not exposed as a free particle. After the break, you again have only color-neutral hadrons. No isolated quark, no isolated gluon. This is what confinement really means in practice. You cannot peel off a single quark or a single gluon and send it across a detector the way you can send an electron across a vacuum tube. When high-energy collisions try to produce bare quarks or gluons, they immediately fragment into showers of hadrons. The underlying quarks and gluons are called protons in this language. You only ever see their fingerprints, not the raw objects. The key question then is this just a model we like, or is it actually forced on us by experiments? Look at deep inelastic scattering, where high-energy electrons are fired at protons. This was done at places like SLAC in the United States and DZ in Germany. The electrons hit the proton with tens of billions of electron volts, probe deep inside, and knock around the internal constituents. If quarks and gluons could fly out freely, you would expect the detector to see clean single tracks corresponding to these point-like partons. But that never happens. What the detectors record are sprays of hadrons, pions, kaons, protons, and other composite particles. These sprays have well-defined patterns. The number of particles, their energy distribution, the angles at which they come out all follow regular trends. The data is extremely well described by models where you start with quarks and gluons, let them radiate more gluons as they move, then force everything to recombine into color-neutral hadrons through a confining string-like mechanism. This process is called hadronization. There are detailed string fragmentation models that take an initial set of partons and produce a simulated spray of hadrons. When you tune these models based on quantum chromodynamics and string tension values around that 1 billion electron volts per femtometer, the output matches real collider data: event shapes, jet multiplicities, momentum spectra. If you try to build a model where quarks and gluons remain free for any significant distance, it simply does not match what detectors see. So confinement is not just a story, it is locked into the way particles appear in high-energy experiments all over the world. And yet, even with that success, there's a deep problem. Why is it so hard to write down a clean, exact explanation of confinement from the underlying equations? On paper, quantum chromodynamics is a local quantum field theory with a well-defined Lagrangian. At high energies, where the strong coupling is small, you can use perturbation theory. That means you expand in a small parameter, and each extra term in the expansion gives a smaller correction. That's how we calculate things like jet rates, scaling violations, and many collider observables. In that regime, QCD works beautifully and gives precise predictions. At low energies, the story changes. As you move to larger distances, around the femtometer and beyond, the strong coupling grows. It stops being a small parameter. The whole perturbative expansion collapses. Adding more and more terms doesn't help. Each term is as large as the last. The mathematics that works for photons in quantum electrodynamics fails for gluons in the infrared regime. You can't just solve for how a proton holds itself together by cranking out a few more terms in a series. To make progress, physicists discretize space-time on a grid and use lattice QCD. They put quark fields on the lattice points, gluon fields on the links, and let a supercomputer sample possible field configurations according to the QCD rules. Then they measure things like the proton mass, the potential between quarks, the temperature where quark-gluon plasma forms. This approach reproduces confinement-like behavior and matches experimental numbers, but it is numerical, not an exact formula. This is the frustrating part. Confinement, the core reason gluons never let go and quarks never appear alone, is something we know is real. We can simulate it, we can test its consequences, but we still don't have a simple, closed-form proof that QCD must confine. The strongest force in nature is one we mostly understand through brute force computation, not through neat equations on a single page. And that raises an even sharper question. How can the same theory that traps quarks so brutally at femtometer scales also let them behave almost free when they get extremely close together? And what does that say about the gluon field at very high energies? How can one force be brutally strong when you look from far away, but get weaker when you zoom in closer and closer to the particles that feel it? In ordinary life, that sounds wrong. Gravity pulls harder the closer you are to a planet. A magnet grabs an iron nail more strongly when it's almost touching. Electric forces between two charges get stronger as the distance shrinks. You're used to closer means stronger. The strong force does the opposite at very short distances, and the reason is buried in how gluons behave. In quantum field theory, a force is not just one fixed strength. It has a coupling, a number that tells you how hard the particles interact. That number depends on the energy of the process, or, which is basically the same thing here, the distance scale you're probing. Physicists call this the running of the coupling. For the strong force, we call the coupling alpha S, and it changes a lot as you move from large distances to tiny ones. At energy scales around the mass of the Z boson, about 91 billion electron volts, alpha S is roughly 0.118. That's a modest value, small enough that our usual calculation methods work very well. At lower energies, near 1 billion electron volts, alpha S is more like zero point 0.3 or zero point 0.4 and can be larger as you go even lower. That is a strong interaction in the technical sense. The expansion we rely on starts to break down. Translate that into distances. High energy means very small distance. At distances around 10 to the power negative 18 meters and smaller, far below the size of a proton, quarks inside look almost free. They still interact, but the coupling is small, and they move as if they're not strongly tied down. At distances around 10 to the power negative 15 meters, the scale of a proton size, the coupling is big, and the quarks are locked into a cage of gluon fields. So the same quark-gluon system that looks like a hard, indivisible object at one scale looks like a loose swarm of almost free partons when you hit it hard enough. That strange personality shift is what asymptotic freedom is about, and it's not just a theoretical curiosity. It showed up very clearly in the data from the first deep inelastic scattering experiments. Back in the late 1960s and early 1970s, at SLAC in California, physicists fired high-energy electrons at protons with energies of tens of billions of electron volts. These electrons are tiny probes. By looking at the angles and energies of the scattered electrons, you can infer what the inside of the proton looks like to that probe. If the proton were a smooth blob of charge and mass, the scattering pattern would be simple and diffuse. But that's not what they saw. The data looked like the electrons were bouncing off small, point-like objects inside the proton. The angles and energy loss pointed to hard, localized hits, as if the proton contained several tiny, concentrated targets. These were the quarks. More than that, the way the scattering changed as you dialed up the momentum transfer told you something else. At very high momentum transfer, those internal objects behaved almost like free particles. They were not bound in the way you would expect if the strong force just kept getting stronger at shorter distances. Instead, experiments show a clear parton structure. The proton behaves in those high-energy collisions as if it contains several quasi-free particles that share its momentum. The pattern of how that structure changes with energy, how the distribution of quarks and gluons shifts as you go to higher momentum transfer, matches the QCD predictions with a running alpha S. At low energies, quarks are stuck. At extreme energies, they can move with almost no resistance over tiny distances before confinement reasserts itself. So you're left with a proton that is two very different things depending on how you look at it. At distances around 10 to the power negative 15 meters, the proton behaves like a solid, unbreakable object held together by a confining flux of gluon field. At distances around 10 to the power negative 19 meters, in very hard collisions, it looks like a busy swarm of quarks and gluons, almost free particles zipping around inside. The same gluon field is responsible for both behaviors. Its self-interaction locks quarks in at large distances and frees them at very small ones. This dual nature is not just a curiosity on a blackboard. It shows up directly in the way high-energy collisions look in our detectors. When you smash protons together at TeV energies, you literally see these almost free partons being kicked out and then forced by confinement to turn into jets of hadrons. The next obvious question is, if you never see a single gluon on its own, how do you actually prove it's there, and not just a clever story theorists tell themselves? If you never see a single gluon on its own, how do you actually prove it's there, and not just a clever story theorists tell themselves? The place where this gets real is in the highest energy collisions we can make. At the Large Hadron Collider, protons are accelerated to energies of up to 6.5 tera-electron volts each, then smashed together for a total collision energy of up to 13 tera-electron volts. That's about 13,000 billion electron volts, more than 13,000 times the rest energy of a single proton, dumped into a tiny region of space that's smaller than an atomic nucleus. In ordinary terms, each proton is just a tiny speck with a mass of about 1.7 times 10 to the negative 27 kilograms. But at the LHC, it carries so much kinetic energy that if you scaled it up, it would be like a small object moving fast enough to reach a significant fraction of light speed, about 300,000 kilometers per second, roughly 186,000 miles per second. That energy does not come from the proton's mass. It comes from the accelerator doing work on it lap after lap in a circular track until it's at ridiculous speed. When two of these protons collide head-on at several tera-electron volts, you don't really have proton hitting proton as solid balls. You have one of the quarks or gluons inside one proton slamming into a quark or gluon inside the other. These internal particles, the partons, take some fraction of the proton's momentum. When they collide, they can be kicked out with hundreds of billions of electron volts each. A single heart scattering can take a quark that was confined inside the proton and send it flying out of the collision region. The same thing can happen to a gluon. But as soon as they move away from the collision point, confinement kicks in. They cannot stay as naked partons. The strong force field between them and the rest of the system ramps up. Gluons are radiated and the whole thing starts to fragment. So the next question is, if the detector never sees a bare quark or a bare gluon, what does it see instead? It sees jets. A high-energy quark or gluon does not make one clean track. It turns into a cone of hadrons, mostly pions and kaons and other light particles, all flying in roughly the same direction as the original parton. The detector records many charged tracks in the tracking system and energy deposits in the calorimeters, clustered into these collimated sprays. Now, quark-initiated jets and gluon-initiated jets are not identical. Because gluons carry more color charge than quarks, they radiate additional gluons more easily as they move. Each of those gluons can split again, then hadronize. The result is that at the same jet energy, gluon jets tend to have more particles and be a bit lighter than quark jets. At typical LHC energies, if you look at jets of the same total energy, gluon jets can have about 30 to 50% more charged particles on average than quark jets. So if a quark jet at some energy has around 20 charged tracks, a gluon jet in the same energy bin might have around 25 to 30. The exact numbers depend on the analysis, but the trend is robust. Gluon jets are busier. Experiments measure the angular spread of jets, how the energy is distributed inside the cone, and the multiplicity of charged particles. They then compare those measurements to detailed simulations based on quantum chromodynamics. In those simulations, you can switch on and off specific features, like the larger gluon color charge that controls how often gluons radiate. When you use a full QCD rules, including gluon self-interaction, the predicted shapes and multiplicities line up with what the detectors see. But you might ask, how do you know you're not just tuning a complicated model to fit anything, instead of testing a specific property of gluons? This is where event shape observables and older experiments like LEP come in. At the Large Electron-Positron Collider, also at CERN, electrons and positrons were collided at energies up to about 200 billion electron volts. In those collisions, the initial state is very clean. One electron and one positron annihilate to produce, for example, a quark-antiquark pair. Those quarks then radiate gluons, and you can get 2 jet events, 3 jet events, and more. Physicists define quantities like thrust, which measures how collimated the event is along a single axis, and sphericity, which measures how spread out the energy is in all directions. They count how many jets appear in each event and at what angles. All of these observables are sensitive to the pattern of gluon radiation, and thus to the color factors that tell you how strongly quarks and gluons emit gluons. QCD predicts specific values for these color factors. For quarks, the effective color factor is a bit more than 1. For gluons, it is roughly twice that. If you plug those values into the theory and use them to compute event shapes and jet rates, you get curves that match the LEP and LHC data across many different observables. If you artificially remove gluon self-interaction from the theory or change the relative strength of gluon and quark radiation, the predictions fall apart. The number of 3 jet events is wrong. The distribution of thrust is wrong. The angular correlations between jets are wrong. So it's not that you can just tweak the model to do anything. The presence of gluons with specific properties, including their self-interaction and their larger color charge, is required to make the numbers match. That's a strong quantitative check that you are really seeing gluon physics in the data, even though no detector ever registers a gluon hit directly. Still, from an experimental point of view, you never see gluon printed on a screen. So how do physicists actually reconstruct what happened in a collision, step by step, starting from nothing but detector signals? A modern collider detector is basically a layered instrument. Closest to the collision point, you have the tracking system. It sees charged particles as they curve in a magnetic field, letting you reconstruct their momentum and direction. Outside that, you have electromagnetic calorimeters that measure the energy of particles that interact electromagnetically, like electrons and photons. Beyond that, you have hadronic calorimeters that absorb and measure the energy of strongly interacting particles like protons and pions. Then you have muon systems further out, because muons can punch through a lot of material. When a collision happens, the detector records hits in all these subsystems. Reconstruction software takes those raw hits and turns them into tracks and energy clusters. Then, jet algorithms group those into jets, cones and angle energy space that correspond to the sprays we talked about. From the jets, physicists infer the energies and directions of the original quarks and gluons that initiated them. On top of that, there are sophisticated simulations called Monte Carlo generators. They start from a theory prediction for the hard scattering of quarks and gluons. Then they simulate gluon radiation, parton showers, confinement, hadronization, and finally the detector response. You can compare these simulated events to real data at every step: jet counts, event shapes, particle multiplicities, energy flows. If you try to build a model without gluons, or with gluons that do not self-interact, or with the wrong number of gluon types, those comparisons fail. Cross-sections come out wrong, shapes are off, correlations do not line up. Only when you put in gluons with specific properties demanded by QCD do you get the right answer across the board. So even though a gluon never appears as a clean line in a detector image, its fingerprints are everywhere, in how many jets you see, how wide they are, how many particles they contain, and how energy is distributed in an event. The fit between QCD and all of that data is the experimental proof that this unruly particle, which never travels alone, is real. And if gluons can control the pattern of entire events at tera-electron volt energies, there's a deeper question waiting right underneath that. How much of the stuff you call mass is actually just this gluon activity, and how much of your own weight on a scale is really gluon energy locked inside protons? When you ask where your mass actually comes from, the numbers point to something very different than what you expect. Start with one proton. Its rest energy is about 938 mega-electron volts, which matches a mass of about 1.67 times 10 to the minus 27 kilograms. That's the standard number in every physics table. Now look inside that proton, at the three valence quarks you're told about in basic particle diagrams, 2 up quarks and 1 down quark. The up quark has a rest mass of roughly 2.2 mega-electron volts. The down quark is a bit heavier, around 4.7 mega-electron volts. So 2 ups plus 1 down gives you about 2.2 plus 2.2 plus 4.7. That's roughly 9 mega-electron volts in total. Compare that to 938. You're missing more than 900 mega-electron volts. The three constituents you were told about only account for about 1% of the proton's mass. So the first blunt conclusion is the proton does not weigh what its quarks weigh. If you treated the proton like 3 little marbles sitting in a box and just added their rest masses, you would get the wrong answer by a factor of 100. Something else has to be providing the other 90+%. The missing mass is not some hidden fifth quark, and it's not a simple mechanical binding energy like a compressed spring in a watch. It comes from energy stored in motion and fields. More specifically, it comes from the kinetic energy of the quarks whizzing around inside, plus the energy density of the gluon field that holds everything together. Here's the key idea. Energy and mass are two ways of talking about the same thing. When you have energy trapped in a system, energy that cannot just fly away, it shows up as mass. When people write energy equals mass times the speed of light squared, this is what they mean in practice. The gluon field inside a proton is constantly active, constantly interacting. That activity stores energy in a tiny volume, and because that energy is confined, it behaves as mass. Inside the proton, the valence quarks are not sitting still. They have significant momentum. They bounce around with speeds close to the speed of light, within a region smaller than a femtometer, that is a quadrillionth of a meter, far less than a trillionth of an inch. That motion contributes kinetic energy. On top of that, the gluon field, which carries a strong force, is self-interacting and dense. It's like having a very intense, highly structured field filling the proton's volume. That field energy is large. If you add up the quark's kinetic energy, the energy stored in the gluon field, and the contributions from short-lived C-quarks and antiquarks popped out of the gluon field, you get almost the entire 938 mega-electron volts. The tiny 9 mega-electron volts from the bare quark masses are just a small correction. So when you hold a chunk of matter in your hand, almost all of its rest mass comes from this internal strong force energy, not from the intrinsic masses of the quarks. You can see how extreme this is if you scale up. Take a person with a mass of 70 kilograms, roughly 154 pounds. Nearly all of that mass is in protons and neutrons inside atomic nuclei. The bare quark masses account for only about 1% of each nucleon's mass, so maybe well under a kilogram of your body's mass is bare quark mass. The other 69 kilograms, more than 150 pounds, is energy stored in quark motion and gluon fields that cannot escape. You walk around every day carrying tens of trillions of joules of confined strong force energy just so your atoms can exist. That might sound like hand-waving, so the natural question is, can you actually calculate a proton's mass from the underlying theory and see this effect come out? Or is this just a story attached after the fact? This is where lattice QCD comes in. Quantum chromodynamics in continuous spacetime is very hard to solve directly at the scales where confinement matters. The strong coupling is large, the usual series expansions fail, so physicists put spacetime on a grid, a four-dimensional lattice. Think of a box a few femtometers across, divided into many tiny cells. Each grid point carries quark fields. Each link between points carries gluon fields. You set the spacing of the lattice to something like 0.05 to 0.1 femtometers, so the grid captures both short distance and long distance behavior. Then you let a supercomputer evolve this system using the QCD rules. It samples many possible configurations of quark and gluon fields that are allowed by the theory. From those samples, you measure quantities like correlation functions, which tell you how a proton-like disturbance in the fields propagates. From that, you can extract the mass of the proton in units of the lattice spacing and fundamental parameters. These simulations are heavy. They use petaflop-scale machines, meaning about 1,000,000 billion floating-point operations per second, running for weeks or months. The raw output is not a pretty formula, it's a set of numbers. But when you convert those numbers back into physical units, you get a proton mass of about 938 mega-electron volts, with a few percent uncertainty, in line with experiment. And here's the important part for gluons. This agreement only happens if you include full gluon dynamics, including their self-interaction and their ability to generate quark-antiquark pairs. If you try to build a lattice model where gluons behave like simple, non-self-interacting messenger particles, like photons do in a first approximation, the calculated mass spectrum would not match reality. Nucleon masses, meson masses, the whole pattern of hadrons would come out wrong. So the fact that lattice QCD gets the right proton mass, starting from quarks and gluons and no extra ingredients, is strong evidence that most of the mass is gluon energy plus quark motion is not just a slogan. It's what the theory actually produces when you let it run without shortcuts. Now go back to that bathroom scale. When you stand on it and see 70 kilograms, the number you're looking at is dominated by quantum chromodynamics, not by the bare masses of fundamental particles. Your weight in newtons, your effective load in pounds, is mostly the Earth's gravity acting on trapped strong force energy. The gluon field inside every proton and neutron in your body is what the scale is responding to. Seen that way, every time you talk about losing weight or gaining mass, at a deep level, you're talking about rearranging where that strong force energy sits, how many nucleons you have, how much confined gluon energy you carry around. You're built out of confined color fields that will not relax. The universe's strongest interaction is the one setting your baseline mass. And that leads directly to the next question. If so much of your mass is stored in the configuration of the gluon field, how exactly is that field shaped inside hadrons? And why does it behave more like a tight, narrow string than a smooth, spreading field when quarks try to separate? Why do strong force fields bunch into ropes instead of fading smoothly into space the way electric fields do? Take a single electric charge. In electromagnetism, the field lines spread out in all directions. Double the distance from the charge and the strength drops by a factor of 4. Move 10 times farther away and the strength drops by a factor of 100. The field dilutes. If gluons behaved like photons, you would expect the force between two quarks to weaken in the same way as you separate them. But that is not what the data shows at distances that matter inside hadrons. When you look at the potential energy between a quark and an antiquark at hadronic scales, around a femtometer and above, it does not flatten out or fall off. It grows roughly in direct proportion to the distance. Stretch them to twice the separation, you roughly double the potential energy. That means the force between them is approximately constant over that range, like a perfectly stiff spring that never gets any easier or any harder to pull. That behavior is completely different from the spreading field picture of electromagnetism, and it's the first sign that the gluon field prefers to concentrate. In quantum chromodynamics models and in lattice simulations, when you place a quark and an antiquark some distance apart and ask, what does the color field actually look like between them? You do not see a gentle cloud, you see a narrow tube of field running between the two, a concentrated channel of color flux, only about a femtometer thick. Outside that tube, the field is comparatively weak. Almost all of the strong force energy is squeezed into this rope-like region. The important consequence is how energy scales. The amount of energy stored in that tube is basically proportional to its length. Double the separation, double the energy. The proportionality constant is the string tension, and for QCD, it's around 0.9 giga-electron volts per femtometer. So if you stretch the tube to 2 or 3 femtometers, around 2 to 3 times 10 to the minus 15 meters, you're storing a few billion electron volts of energy in that tiny region. That's enough to create new quark-antiquark pairs. At that point, the system decides it's cheaper to break the tube and form new hadrons than to keep stretching it. So this flux tube picture is not just a visual aid. It directly explains why the strong potential grows linearly with distance at these scales, why the force stays roughly constant, and why hadronization kicks in as soon as you try to separate colored objects a few femtometers apart. The field is not filling space, it's pulling itself into a narrow channel and resisting separation by loading up energy per unit length. You can see evidence for this string-like behavior very clearly in systems that are cleaner than a messy proton, namely heavy quarkonium. These are bound states of a heavy quark and its own antiquark. Charm plus anticharm gives charmonium. Bottom plus antibottom gives botonium. Because the quarks are heavy and move more slowly than light quarks, their bound states are easier to treat with potential models. If the strong force between the heavy quark and antiquark were purely like electromagnetism, the potential would be dominated by a term that decreases with distance, similar to the Coulomb potential in atoms. But when you measure the actual spectrum of charmonium and botonium in electron-positron colliders, you do not get just that pattern. You get a sequence of states whose spacings fit much better with a potential that has two parts. One part that looks like a Coulomb term at short distance, and another part that grows linearly at larger separation. This combined Coulomb plus linear potential is a standard way to describe the heavy quark potential in QCD. The Coulomb-like part dominates when the quark and antiquark are very close. The linear string-like part dominates when they are farther apart. When you plug this into the equations and solve for the allowed energy levels, the predicted masses of the various quarkonium states line up closely with the measured resonance peaks and collider data. The fine details of the spectrum, which states appear where and how they are spaced, are strong evidence that the strong force acts string-like at the relevant distances. This is not a vague story. The actual positions of states like the J/psi, the psi prime, the upsilon family, and their excitations all point back to a potential with a genuine string tension. Change that tension, remove the linear part, and the level pattern stops matching experiment. Keep it, and the match improves. Those measured spectral lines are a direct observational probe of how the gluon field confines, without ever seeing the field itself. Historically, this behavior is why the idea of string tension entered hadron physics long before modern string theory. When physicists plotted the squared masses of hadrons against their spin, they found approximately straight lines called Regge trajectories. That kind of pattern is exactly what you get if you model hadrons as rotating strings with a fixed tension. The number that falls out of those fits is around that same 0.9 giga-electron-volts per femtometer. The strong force seems to organize itself as if colored objects are connected by tiny, relativistic strings. It is tempting at this point to just say, so QCD is strings, and stop there. But that would be too simple. QCD is a quantum field theory of quarks and gluons. The string-like behavior we see is an emergent property of that field theory in the low-energy, long-distance regime. At very short distances, the language of point-like quanta and running couplings works well. At longer distances, the same theory produces flux tubes with a well-defined tension. String models are a very useful, effective description, but they are not the full microscopic story. The important point for the gluon is this: a field built from self-interacting gauge bosons with the right symmetry and coupling naturally produces geometric structures like tubes and strings. The gluon field is not just a fog of particles being exchanged. It can lock into narrow, persistent configurations that behave like physical objects with tension and length. That is already far away from the simple force carrier picture you learn from photons. And once you accept that the gluon field can concentrate itself, tie up into tubes, and store huge amounts of energy per unit length, the next question is obvious and sharp. What is it about gluons that lets them do this while photons remain so well behaved? And how does their ability to interact with each other directly twist the rules you thought field had to follow? How much can you really trust your picture of a field if one version just flows through itself and another one collide with itself non-stop? Take light first, because that's the clean case. In classical electromagnetism, two light beams can cross an empty space and nothing special happens. A laser pointing left and a laser pointing right can pass straight through each other, and each one keeps going as if the other isn't there. The electric and magnetic fields add up in the math, then separate again. There's no permanent trace of the encounter. In quantum electromagnetism, the quantum version of this, photons technically can interact with each other, but only through rare higher-order processes where they briefly turn into virtual charged particles and then back into photons. There is no basic, built-in interaction where 3 photons meet at one point or 4 photons meet at one point in the simplest Feynman diagrams. The underlying symmetry group, called U1, is abelian, which basically means the field does not carry its own electric charge. Photons are neutral, so they don't act as direct sources for more photons. That's why QED is so clean. At everyday energy scales, light mostly ignores other light. You can think of the electromagnetic field as something that responds to charges and currents, not something that decides to clump or collide by itself in empty space. Now contrast that with gluons. Here, the basic rule is completely different. Gluons carry color charge, the very charge of the strong interaction. So in quantum chromodynamics, the field is charged under its own symmetry. The math for this is non-abelian, based on the SU3 group, and one direct consequence shows up the moment you draw the allowed interaction points. Right at the fundamental level, QCD has vertices where 3 gluons meet and vertices where 4 gluons meet. These are not rare, higher-order loop effects. They're present in the leading diagrams. That means gluon fields interact with themselves even if there are no quarks around. The field doesn't just respond to external color charges. It is a color charge. Inside a proton, this changes everything. You don't just have three valence quarks sending gluons back and forth in a tidy way, you have gluons radiating more gluons, gluons scattering off each other, gluons splitting into quark-antiquark pairs and recombining. The result is a dense, turbulent gluon field. The proton is not three quarks plus a couple of simple force lines, it's a many-body system of quarks embedded in a self-interacting sea of gluons. The obvious question is, can you see the effect of these 3 gluon and 4 gluon interactions in data, or is this just something that lives on Feynman diagrams? Collider events with multiple jets are one of the cleanest places to test this. In electron-positron collisions, for example, you start with a very simple initial state. An electron and a positron annihilate, often producing a quark-antiquark pair. If QCD only had quarks exchanging photon-like gluons that didn't self-interact, you would mostly expect 2 jets back-to-back, one from the quark, one from the antiquark, with a certain distribution of energies and angles. But experiments at LEP and other colliders see a lot of 3-jet events. Those are naturally explained by a quark or antiquark radiating a high-energy gluon, which then produces its own jet. The rate and angular distributions between those jets are not arbitrary. They depend very specifically on the color factors associated with quark-gluon and gluon-gluon interactions. When you plug in the SU3 values, with gluons carrying more color charge and self-interacting, the predicted 3-jet rate and the angular distributions between jets match what the detectors see. At higher energies and in more complicated environments like the LHC, you can look at events with several jets and at subtle angular correlations between groups of jets. These observables are sensitive to whether gluons can interact directly with each other or only via quarks. Run the QCD calculations with the proper 3-gluon vertex included, and the predictions line up with measurements of multi-jet cross-sections and event shapes. Force the gluons in the theory to behave like photons, no direct self-interaction, and the agreement collapses. You get the wrong number of jets, the wrong angle patterns, the wrong distributions. So the self-interaction is not optional. It's not a decoration. It's a necessary ingredient to match real collision data. This brings you to a deeper shift in how you think about fields. You're used to the idea that a field just fills space and responds to sources. Turn on a charge, you get an electric field around it. Turn off the charge, the field goes away. The field itself is a kind of stage, and the charges are the actors. The gluon field refuses to stay on that level. Because it carries its own charge, it behaves as both stage and actor. It doesn't just sit there until quarks tell it what to do. It generates structure on its own. Flux tubes, localized regions of high field strength, complicated vacuum configurations. In QCD, even what you call empty space isn't really empty. The vacuum has non-trivial gluon field configurations fluctuating all the time, with something like a gluon condensate contributing to the energy density of the vacuum. This is why talking about confinement or flux tubes without mentioning self-interaction is incomplete. The reason the field bunches into tubes, the reason the potential between quarks grows linearly at hadronic scales, the reason mass emerges from gluon energy, all trace back to the fact that gluons are charged under their own interaction and can collide, merge, and create more of themselves. The strong force doesn't just transmit. It reorganizes itself, and in doing so, it rewrites the structure of space at femtometer scales. So once you accept that the gluon field constantly produces more gluons, and that these gluons collide and recombine, the obvious next step is, if you crank the energy higher and higher, probe the proton harder and harder, does this gluon multiplication just keep growing without limit? Or is there a new regime where the gluon density becomes so high that the field changes phase again? When you keep dialing up the energy on your probe, how long can the proton keep revealing more structure before something fundamentally different happens? In scattering language, you describe the partons inside a proton by how much of the proton's momentum they carry. That fraction is called x. Big X means the parton is carrying a large chunk of the proton's motion. Small x means it's carrying just a tiny slice. When you fire higher and higher energy electrons at a proton with hundreds of billions of electron volts, you access smaller distance scales and, at the same time, smaller values of x. What experiments find is that as you go to smaller and smaller x, the number of gluons you effectively see goes up very fast. You don't just see a mild increase, you see the gluon distribution rising steeply as x gets tiny. In other words, at very high energies, the proton contains a huge number of very low momentum gluons. From the parton point of view, it's like you keep zooming in, and every time you do, there are more gluons packed in than you expected. This can't keep going forever in a simple, unlimited way. If the gluon density just kept rising without any balancing effect, cross-sections would grow past basic unitarity bounds. Also, at some point, the gluons are so numerous and so close that they cannot be treated as independent particles anymore. Their self-interactions become important, not just in pairs, but as a collective effect. Gluons start to recombine as quickly as they are radiated. This is where the idea of gluon saturation comes in. At very small x and high energies, the gluon density inside a fast-moving proton or nucleus can become so large that a new regime appears. Instead of a dilute gas of independent gluons, you get a state where the fields are strong and coherent over extended regions in the plane transverse to the motion. The theory framework built to describe this is called the Color Glass Condensate. The name sounds fancy, but the core picture is concrete. Color refers to the strong charge. Glass refers to the fact that some degrees of freedom evolve slowly compared to the scattering time, like atoms frozen in a glass, while others respond quickly. Condensate reflects that you have a high occupation number of gluons in certain modes, acting more like a classical field than like individual quanta. In this regime, the proton or nucleus, in its own rest frame, still has its usual size, around a femtometer. But in a frame where it's moving with ultra-relativistic speed, it looks like a flattened sheet of dense gluon field with a characteristic saturation momentum scale that sets how hard you have to hit it to resolve individual partons again. This is not just theoretical speculation. Experiments have been pushing into this small x regime for decades. At HERA in Germany, electrons were scattered off protons over a wide range of energies. They measured structure functions, in particular one called F2 as functions of x and the momentum transfer. As x got very small, F2 rose steeply, which is widely interpreted as evidence that gluon densities are increasing rapidly in that region. As you go deeper into low X, models that include saturation begin to describe the data better than models that assume a simple linear evolution of gluon numbers. At the LHC, you can look at proton nucleus and nucleus collisions at tera-electron-volt energies. In these systems, the nuclei are made of many protons and neutrons, so the effective gluon density in the transverse plane is even higher. Certain patterns emerge, especially in particles produced at forward rapidities, that are consistent with saturation. You see modifications in the number and distribution of produced particles that hint that gluons are recombining as well as splitting. In heavy ion collisions, where you smash large nuclei like lead into each other at multi-TeV energies, the overlap region between the two nuclei behaves to a good approximation like a black disk of saturated gluon field. Black here means that anything that tries to pass through that region, any parton, will interact with probability close to 1. The system is so dense that it looks opaque to colored probes. The initial state just before the collision can be treated, in many models, as two sheets of color glass condensate colliding. So at this point, your tidy picture of a proton as 3 quarks held by gluons has been completely inverted at high energies. At low energies, in nuclear physics and chemistry, it's useful to say 3 quarks in a proton, 3 in a neutron. At LHC energies, at 7 or 13 tera-electron volts, that picture is no longer the right starting point. The proton is better described as a big fluctuating gluon system with a sea of quark-antiquark pairs. The 3 valence quarks are still there, but they are more like tags on top of a dense gluon background. In other words, Crank up the energy, and the proton turns into a gluon-dominated object. Its identity is controlled by the gluon distribution at small x, by how that distribution saturates, and by how the color glass condensate evolves into the hot matter created in the collision. The quarks become subdominant actors in a play run by gluon fields. That raises a sharp next question. If at extreme energies, the proton or nucleus is effectively a sheet of saturated gluon field, what happens right after two of those sheets collide head-on? And can that collision actually melt protons and neutrons into a new state of matter where quarks and gluons are no longer confined at all? How far can gluons go if you push them past the point where protons and neutrons even exist? In heavy ion collisions, that's exactly what happens. At RHIC in the US and at the LHC at CERN, we don't just collide protons, we collide whole nuclei, like gold on gold or lead on lead. Each nucleus carries trillions of electron volts of energy per nucleon, all focused into a tiny region smaller than an atom. When they hit head-on at close to the speed of light, the overlap zone turns into a tiny fireball. The temperatures in that fireball reach around 4 trillion Kelvin. Written out, that's a 4 with 12 zeros. For comparison, the sun's core is about 15 million Kelvin, so you're looking at something like 250,000 times hotter than the center of the sun. At those temperatures, the energy density is so high that protons and neutrons cannot survive as bound states. The kinetic energy and gluon field energy overwhelm confinement. Quarks and gluons are no longer tied into individual hadrons. Instead, you get a deconfined state called quark-gluon plasma. This fireball is tiny. Its size is a few femtometers across, roughly the diameter of a large nucleus. So we're talking about something like 10 to the minus 15th meters, about a millionth of a billionth of a millimeter. It also expands and cools extremely quickly. The whole quark-gluon plasma phase lasts on the order of 10 to the minus 23rd to 10 to the minus 22nd seconds. But in that short time, gluons are no longer confined ropes between quarks. They form a bulk medium with quarks embedded in it, and you can study its properties from the particles that fly out as it cools. The surprising part is how this stuff behaves. With a temperature of trillions of degrees, you might expect a gas of almost free quarks and gluons, something close to an ideal gas. That's not what the data shows. The quark-gluon plasma acts like a liquid, and not just any liquid, a very efficient one. Its viscosity, the thickness that resists flow, is extremely low when you scale it by its entropy density. That ratio is close to a theoretical lower bound that people guessed from calculations in strongly coupled quantum systems and certain gravity models. In the collisions, the heavy ions do not always overlap perfectly symmetrically. Many collisions are more like two flattened disks hitting slightly off-center. That gives an almond-shaped overlap region. If the medium were a simple gas of weakly interacting particles, the final particle distribution would keep a lot of random noise. Instead, you see a very clear collective flow pattern. More particles come out along the short axis of that almond shape than along the long axis. This is called elliptic flow, and it's quantified by a parameter called V2. Higher order patterns related to smaller geometric fluctuations show up as V3, V4, and so on. Hydrodynamic models, where you treat the quark-gluon plasma as a fluid with low viscosity, reproduce these flow coefficients very well, both at RHIC and at the LHC. That tells you the medium is not just a chaotic spray of independent partons. The gluon field is organizing into a collective, floating state that carries pressure and transmits it efficiently across the tiny system before it freezes out into hadrons. There's another strong clue: jet quenching. In the same heavy ion collisions, you also produce high-energy quarks and gluons that want to fly out as jets, just like in proton-proton collisions. But when those partons try to escape through the hot medium, they lose energy. They scatter off the gluons and quarks in the plasma and radiate additional gluons. By the time they emerge, their jets are weakened or even partially missing compared to what you would expect if there were no plasma. At RHIC and the LHC, analyses show that partons can lose several giga-electron volts of energy while crossing just a few femtometers of quark-gluon plasma. That's like taking a bullet and having it lose most of its speed after passing through a sheet of material only a few atoms thick. It tells you that the medium is extremely dense in color charge. The gluon field in this state is not gentle, it's opaque to colored probes at these energies. So on one hand, you have strong collective flow, indicating a near-perfect fluid. On the other hand, you have strong jet quenching, indicating a dense medium that interacts hard with any high-energy parton trying to pass through. Both of these point to the same conclusion. The quark-gluon plasma is a strongly coupled liquid of quarks and gluons, not a thin gas of weakly interacting partons. The gluon field in this phase controls both the bulk motion and the way individual partons lose energy. Now, step back from the lab and look at the universe. For the first few microseconds after the Big Bang, the whole observable universe was hotter than the temperatures we make at RHIC or the LHC. Everything was in a quark-gluon plasma state. There were no protons, no neutrons, no atomic nuclei. Gluons weren't just internal messengers inside hadrons, they were one of the main degrees of freedom filling space. As the universe expanded, it cooled. When the temperature dropped below a critical range, around 150 to 160 mega-electron volts, corresponding to roughly 1.5 trillion Kelvin, quarks and gluons confined into hadrons. The physics you study in heavy ion collisions is basically a controlled replay of that early phase transition, but compressed in space and time. A fireball a few femtometers across, living for a tiny fraction of a second, gives you information about what the universe was doing everywhere at once when it was less than a microsecond old. So when you look at the flow patterns and jet quenching from lead-lead collisions at the LHC, you're not just seeing hot nuclear matter. You're seeing how the gluon field behaves when it's turned into a fluid and allowed to fill a volume, before confinement reasserts itself. It stops being a set of local strings and becomes a collective background. That's the same transition the real universe went through on a cosmic scale. And that leaves you with a practical problem. If the only way to understand this gluon-dominated matter is to track countless interacting quarks and gluons, and if our usual pencil and paper methods break down, how do you actually do the calculation, and what does it take to simulate this theory faithfully enough to get real numbers out, like the proton mass or the transition temperature? How do you actually do physics when your main theory fails exactly where the interesting stuff happens? With QCD, that's the situation. At very short distances where the strong coupling is small, the math behaves. You can treat interactions as a series of small corrections, calculate diagrams, and the series converges. That's how you handle high-energy jets, scaling violations, all the clean asymptotic freedom stuff. But for confinement, hadron masses, and phase transitions, the coupling is not small, it's large. Your expansion parameter is no longer less than 1. The usual toolbox just breaks. So instead of giving up, physicists change the game. They stop pretending space-time is a smooth continuum they can handle with neat integrals, and they put it on a grid, a 4-dimensional lattice. 3 dimensions of space, 1 of time. You chop a small box of space-time into tiny cells. A typical realistic setup might be something like 64 points along each spatial direction and dozens or more slices in time. The spacing between neighboring spatial points is on the order of 0.1 femtometers, a tenth of a quadrillionth of a meter. On this grid, each lattice site carries quark fields. Each link between neighboring links carries gluon fields. Instead of continuous gauge fields, you have group elements attached to links. The path integral that defines QCD becomes a huge sum over possible values of these fields at all sites and links. You can't do that sum analytically, but you can sample it numerically, configuration by configuration, with Monte Carlo methods. So your picture of a proton becomes a particular pattern of fields on this grid, not 3 dots and some lines. You generate many such patterns according to how likely they are in QCD, and then you measure what a proton-like disturbance looks like across time slices. From how that signal decays in time on the lattice, you read off a mass. That's lattice QCD in plain language, and the only reason you go to this trouble is because gluons in the strong coupling regime leave you no simpler option. That leads to the next question. How much brute force does it actually take just to get one proton mass out of this lattice? The answer is a lot. Simulating a realistic lattice with light quarks, meaning up and down quarks close to their physical masses, is one of the most demanding calculations in physics. You're dealing with millions of lattice sites, each with multiple field components, and you need to generate and analyze thousands of configurations to beat down statistical noise. Each update of the fields, each inversion of the huge matrices that come from the quark part of the action is expensive. To do this properly, you need petaflop scale computers. That means machines capable of 10 to the power of 15 floating point operations per second. Even at that speed, full-blown simulations with physical quark masses and fine lattice spacing can run for weeks or months. That's equivalent to millions of ordinary laptops working flat out, just to tell you what the spectrum of a few low-lying hadrons should be. Out of this mountain of computation, you extract specific quantities: proton and neutron masses, pion and kaon masses, decay constants that describe how likely certain particles are to decay into others. At finite temperature, you can simulate how the system's energy and pressure change, building an equation of state for quark-gluon plasma. None of that comes cheap. Every number requires handling an enormous strongly coupled gluon field on that grid. So the obvious check is, does this machinery actually match what you measure in the lab, or are you just tuning parameters until something fits? Lattice QCD passes that test in a very direct way. When you run these simulations with the right inputs, you get the spectrum of low-lying hadrons, and it lines up with experiment to within a few percent. The lightest meson, the pion, comes out around 140 megaelectron volts. The rho meson lands around 770 megaelectron volts. Nucleons, protons, and neutrons appear near 940 megaelectron volts. These are not put in by hand. They come out of the dynamics of quarks and gluons on the lattice. You can also crank up the temperature in the simulation, effectively by compactifying the time direction, and study how the system behaves as you move from a hadronic phase to a deconfined phase. Lattice calculations predict that the QCD transition is a smooth crossover for physical quark masses, not a sharp first-order phase transition, and that it happens at a temperature around 150 to 160 megaelectron volts. Convert that to ordinary units, and you get roughly 1.5 to 2 trillion Kelvin. Heavy ion experiments at RHIC and the LHC infer from flow and particle yields that the quark-gluon plasma they create appears at around that same temperature scale. The equation of state extracted from lattice QCD, basically the relationship between pressure and energy density, feeds directly into hydrodynamic models of these collisions, and those models reproduce the observed flow patterns well. So you have a direct loop. Theory on a grid predicts numbers, experiments measure numbers, and they match. A crucial detail is that all of this only works when you include gluons with their full self-interactions and non-abelian structure. If you try to simplify QCD into a theory where gluons behave more like photons, with no triple gluon or four gluon interactions, the confinement pattern changes, the hadron spectrum shifts, and the transition behavior at high temperature doesn't line up with heavy ion data. The lattice is not just confirming some strong force, it is confirming QCD with real gluons. That leaves you with an uncomfortable fact about how far gluons push the limits of your tools. For electromagnetism, you can understand the hydrogen atom with pencil and paper methods. You solve a differential equation, you get energy levels, and you can write them down in a closed form. You can calculate the behavior of a meter-long electric field in a lab without any need for a supercomputer. The theory is still quantum and subtle, but it stays manageable. For QCD, the moment you want to understand something as basic as why does a proton have the mass it does, or how exactly does confinement emerge, analytic methods stop being enough. You are forced onto a four-dimensional grid and into industrial-scale numerics. The same underlying type of math, gauge theory, that quietly describes the electromagnetic fields in a motor or a transformer becomes explosively hard when the gauge charge is color instead of electric. That's the signature of how badly gluons refuse to behave like simple messenger particles. They drag you off the blackboard and into a supercomputing center. They turn a basic question about mass and binding into a petaflop-hungry problem. And if a field is that real, that powerful, and that self-contained that it needs this much machinery to handle, it raises a sharp question. Can gluons, with no quarks at all, bind to each other and form their own standalone particles made purely of glue? How far can you push the idea that forces are carried by particles before the force itself turns into the matter? You already know gluons carry color charge and attract each other. They don't just move between quarks, they collide and interact on their own. Once you accept that, a very direct question appears. What stops gluons from binding to each other with no quarks involved at all? QCD says nothing stops that. The theory predicts whole families of bound states, built purely from the gluon fields. These are called glueballs. In QCD language, you can build states with different spins and parities, scalar, tensor, and more, in the same way you build different atomic orbitals in quantum mechanics. But now, the stuff forming the bound state is just the gluon field. Calculations say the lightest glue balls should have masses in the range of about 1 to 3 billion electron volts. That's roughly 1 to 3 times the proton mass scale, but with no quark sitting inside, only gluon energy held together by its own attraction. So the theory side is clear. The strong force is so nonlinear that it can confine itself. But that raises the next hard question. Can you actually predict concrete numbers for these glue balls, or is this just a vague idea that disappears as soon as you ask for details? On the lattice, you can set up QCD in a simplified way, with just gluons and no dynamical quarks. That's called pure gauge theory. In that setup, you look for states that behave like isolated particles made purely of the gauge field. Lattice QCD simulations of this kind repeatedly find a lightest glue ball with a mass around 1.5 to 1.7 mega-electron volts. That's roughly a proton and a half in mass, made entirely from gluon field energy. Those simulations also predict heavier glue balls with different spins and higher masses, forming a whole spectrum, not just a single special case. When you then include quarks in the simulation, you find that these glue ball states can mix with ordinary mesons because they share the same quantum numbers. So in the full theory, what you'd actually see in a detector is not a clean, pure glue spike, but a set of physical particles that are mixtures, some mostly quark-antiquark, some with a big glue component. This is why glue balls are such a headache experimentally. In the real world, you never switch quarks off. So the next step is obvious. Have we seen anything in the data that looks like one of these mixed states with a large glue piece? Experiments at CERN, BEESI, and other facilities have found several suspicious candidates in the mass range where the lattice says the lightest glue ball should live. States like the F0 of 1500 and the F0 of 1710 sit in that 1.5 to 1.7 GeV window, and their properties do not fit neatly into the simplest quark model. If every meson were just a quark plus an antiquark, you'd expect a certain pattern of masses and decays. These particular states have decay branching ratios into pairs of pions, kaons, and eta mesons that look off compared to that simple picture. One way to explain those oddities is to say these states are mixtures, with a significant glue ball component blended with quark-antiquark pieces. Different analyses weight the mixture differently, some saying one state is more glue-rich than the other, but there is no universal agreement. Part of the difficulty is that hadron spectroscopy in this region is crowded, with many overlapping resonances and broad widths. It's hard to isolate a single, narrow, pure glue signature. So right now, the situation is this. Lattice QCD says glue balls should exist and gives you a pretty sharp mass estimate for the lightest one. Experiments see several states in that mass range that look suspicious for a simple quark-antiquark picture, but we do not yet have a universally accepted, clean identification where everyone agrees this one is dominantly a glue ball, case closed. The evidence is strong, but still indirect. That leaves you with the real reason glue balls matter so much conceptually. If we ever pin one down beyond serious doubt, we will have direct confirmation of a very extreme idea. matter made purely from force, no underlying substance beyond the field itself. The gluon field, which you first met as a carrier of the strong interaction, would also be forming the bound states you detect as particles. The role of force carrier and matter would blur. And this is already what QCD is hinting at in other ways. Most of the proton's mass comes from gluon field energy, not quark rest masses. Quark-gluon plasma behaves as a collective fluid where gluons dominate the dynamics. Flux tubes act like strings with tension, storing energy in their length. Glueballs simply push that trend to the limit. No quarks at all, just a self-interacting gluon field forming a localized lump that travels through space like any other particle. So once you start thinking that way, calling the gluon just a force carrier stops making sense. It's a degree of freedom that can build bound states, dominate the mass of ordinary matter, flow like a fluid in yet another regime, and maybe even show up as standalone glue particles in the spectrum. It's the same field in all those roles. But if the gluon field can act as matter at some scales, dominate mass at others, and flow like a fluid in yet another regime, you're forced to ask a tighter question. How does its strength actually change as you move between all these scales? And how does the running of the strong coupling constant knit all of these wildly different behaviors into one consistent story? How can one force have a single name but a different strength every time you change how hard you probe it? For the strong interaction, the key number is the strong coupling, usually written as alpha S. It is not a fixed constant you write down once and then forget. It is a function of energy. At the energy scale set by the Z-Boss mass, around 91 billion electron volts, precision measurements at the LEP collider give alpha S about 0.118. That's a moderate value, small enough that perturbation theory works, and you can trust calculations with a few extra correction terms. Drop the energy down to just a few billion electron volts, and alpha S is not the same. Extractions from tau lepton decays, from jet data, and from deep inelastic scattering give values closer to 0.3 or 0.4, sometimes larger. That's already in the regime where the force is so strong that the series expansion you use at high energy is barely under control. The renormalization group equations, which come out of the quantum field theory formalism, tell you how alpha S changes with energy. They give you a running curve, not a flat line. You can measure alpha S at different reference scales, then run them all to a common scale using that curve and check if they agree. Experiments span almost 3 orders of magnitude in energy, from around 1 GeV up to the Z-mass and beyond, and within uncertainties, they line up on the same running trajectory. That's a non-trivial test that this strength that won't sit still is a real property of the gluon field, not just a fitting trick. Now, look at how many different distance scales live inside one proton. Its radius is roughly 0.8 femtometers, just under a millionth of a billionth of a millimeter. At that scale and above, confinement dominates. Quarks are fully locked in, and the hadron behaves like a solid object. Go down to around 0.1 femtometers, 1/10 of a proton radius. There, quarks are still correlated and confined overall, but the interaction between a pair separated by that distance is already weaker, and perturbative methods start to gain some traction. Push further down to distances around 10 to the power minus 18 or minus 19 meters, that's about 10,000 times smaller than a proton radius, much smaller than a trillionth of a millimeter, and asymptotic freedom takes over. Alpha S becomes small, and quarks behave almost free over those tiny distances. So inside one proton, depending on how closely you look, you see everything from a hard, confining regime to a semi-correlated regime to an almost free regime. It's like having one object that at 1 meter behaves like a rigid steel, at 10 centimeters behaves like a sticky liquid, and at a millimeter behaves like a gas. Only here, the distances are in femtometers and below, not in human units. This scale dependence is not just an abstract curiosity, it's built into how we extract parton distribution functions, the PDFs that tell you how many quarks and gluons carry a given fraction of the proton's momentum. Global fits to PDFs use data from many sources. Fixed target experiments with beam energies of a few tens of GeV, the Hera Electron-Proton Collider at higher energies, the Tevatron Proton-Antiproton Collider, and the LHC at several tera electron volts. For each process, you measure cross-sections and structure functions at certain momentum transfers, which correspond to certain distance scales. Those measurements depend on both the PDFs and the value of alpha S at that scale. When you do a global fit, you're adjusting the PDFs and the running of alpha S so that one set of functions matches all of these different data sets at once. If you try to force alpha S to be a constant, the fit breaks. You cannot simultaneously match the way cross-sections change with energy and the way structure functions evolve with momentum transfer. The so-called scaling violations in deep inelastic scattering, the way distributions shift as you increase Q², are direct evidence that both PDFs and alpha S run. The gluon distribution at small momentum fraction grows as you go to higher Q², and that growth pattern only matches the data if the strong coupling decreases with Q² according to the renormalization group. So the running coupling is not an optional detail. It is required to make the proton's internal structure consistent across all the different ways we hit it, from modest accelerators to the highest energy colliders on Earth. This kills the old picture of the proton as a static billiard ball with three quarks glued in place. In reality, the proton is a dynamic object whose internal makeup depends on the scale of your probe. At relatively low energies, the three valence quarks stand out, and it makes sense to draw a picture with three dots in a bag. As you crank up the energy, the sea of quark-antiquark pairs and gluons becomes more important. At very high energies, the proton looks more like a dense gluon cloud with quark impurities. Change the collision energy and you literally change what the proton looks like in terms of parton content. At one scale, you might say this proton is mostly its valence quarks. At another, you might say this proton is packed with low-X gluons. The gluon field is rewriting the object on the fly, depending on how hard you hit it. Alpha S controls how fast that rewrite happens as you move between scales. All of this is encoded in the same theory, QCD, but the behavior is wildly different in different regimes. At high energy, the math is clean and predictive. At low energy, it becomes strongly coupled and forces us onto numerical lattices. That tension leads straight into a deeper issue, the way we even define and control quantum field theories at all. Because QCD doesn't just have a running coupling, it sits right on the edge where infinities, renormalization, and non-perturbative physics collide. So the next question is sharp. If the coupling can run, and if the math is full of integrals that want to go to infinity, how do we know QCD is even a well-defined theory from top to bottom? And why do gluons sit right on the point where our usual mathematical tools start to show their limits? How do you trust a theory when the raw math keeps trying to blow up to infinity? That's the starting problem with any quantum field theory. When you write down the basic equations and try to calculate physical quantities, like a particle's mass or its charge, the integrals you meet often run off to infinity. Loop diagrams, virtual particles, all of that structure produces terms that at first glance do not make sense. The theory looks sick. Renormalization is the repair job. You introduce a cutoff, you separate the infinities into a few parameters you don't know anyway, and you redefine those parameters in terms of measurable quantities. Mass and charge are no longer bare inputs. They are physical values after you've absorbed the divergences. If this sounds like sweeping infinities under the rug, the key test is whether the predictions that come out the other end match experiment. In QED, this process works almost perfectly. You renormalize the theory, run the coupling with energy, and you can calculate things like the electron's magnetic moment to around 10 decimal places. When you measure that in the lab, you get the same digits. QED becomes the poster child for how renormalization can take a theory full of divergences and turn it into one of the most accurate descriptions of nature we have. QCD uses the same basic machinery, but the story splits depending on which energy range you care about. At high energies, renormalization does something special for QCD. When you include gluon self-interactions correctly and follow the renormalization group equations, you find that the strong coupling shrinks as the energy scale goes up. That's asymptotic freedom. At very short distances, the effective interaction between quarks becomes weak. The expansion parameter is small, perturbative theory converges, and calculations make sense. Life is good in the ultraviolet. Run the same equations down toward lower energies, toward the infrared, and the situation flips. Alpha S grows, the coupling becomes large. The very expansion that saved you at high energy becomes useless at low energy. Each extra term you try to add is as big as the last one. The mathematical trick you relied on stops working. For confinement, hadron masses, and many properties of low-energy QCD, you cannot trust perturbation theory at all. You have to switch to non-perturbative tools like lattice QCD or effective models. So QCD is asymptotically free but non-perturbative in the infrared. The same renormalization group that makes the theory clean and predictive when you zoom in is the one that tells you, as you zoom out, you're on your own. The coupling is too big for these methods. Despite this split personality, QCD still passes hard numerical tests. Alpha S itself has been measured with percent-level precision from very different kinds of processes. Tau lepton decays at an energy scale of about 1.78 billion electron volts give one extraction. Event shapes at LEP at around the Z boson mass of 91 billion electron volts give another. Jet production at the LHC provides measurements at even higher scales. Lattice QCD studies also infer alpha S by matching calculations to hadron properties. Each of these measurements is made at a different reference energy. You then use the renormalization group equations to run them to a common scale, usually the Z mass. If QCD is right, they should converge to the same value within uncertainties, and they do. A value around 0.118 at the z-scale emerges as the common target. That means the theory's description of how the coupling changes from a few GeV to nearly 100 GeV, corresponding to distance scales from about 0.1 femtometers down to a couple of thousandths of a femtometer, is consistent across very different kinds of experiments. That is a serious stress test. It's not one measurement, it's many, tied together by the same running curve. If the renormalization story were wrong, those numbers would drift apart. The fact they line up is strong evidence that in the high-energy regime, QCD works as a quantum field theory with proper renormalization. And yet, right next to that success, you have the glaring gap. We still do not have an analytic derivation of confinement from the QCD equations in continuous spacetime. We don't have a closed-form solution that says, here is why quarks and gluons can never be isolated. We have proofs in simplified models, strong numerical evidence on the lattice, but not the kind of compact argument you can write on a page. For something as basic as why is a proton a bound object with a mass of 938 MeV, we rely on gigantic numerical simulations, not a neat formula. So QCD sits in a strange place. On one hand, it is one of our best tested theories. We predict alpha S running, jet rates, scaling violations, quark-gluon plasma behavior, hadron spectra, and the numbers match. On the other hand, for its most iconic feature, confinement, we still lack a rigorous analytic proof. The gluon, the particle responsible for the strongest force in nature, is exactly the thing that pushes our mathematical tools up against their limits. You can think of it this way. The same field that lets you compute high-energy observables with near-absurd precision is also the field that refuses to give up a simple explanation of why matter is bound at all. The particle that glues your world together is also showing you where the seams are in the theoretical framework you're using to describe it. So the obvious next question is, if the current machines and methods have taken us this far, to asymptotic freedom, to quark-gluon plasma, to hints of glueballs and saturation, what are we building next? And which unanswered gluon questions are sharp enough that entire new colliders are being designed just to go after them? Right now, we can test the strong force to a few percent, but we still can't answer basic questions like what is exactly inside a proton at very small x, or what does confinement look like in detail. So the next step is pretty direct. Build a dedicated gluon microscope. That's what the electron-ion collider is for. Instead of smashing protons into protons like the LHC, you smash electrons into protons and into heavy nuclei at energies of a few tens of billions of electron volts, but with extremely high luminosity, meaning an enormous number of collisions per second. The electron is a clean probe. It only interacts electromagnetically, so you can use it to scan the internal structure of the proton without adding more strong force mass from the probe itself. By varying the electron energy and the scattering angle, you can dial in the resolution. You want to get down to distance scales around 10 to the minus 19 meters. That's 10 times smaller than the distances probed in many classic deep interactive experiments, about 10,000 times smaller than a proton radius, and obviously far below anything on human scales, feet or inches. At those scales, you're looking right into the small x region, where gluons dominate. The goal is to map in detail how many gluons sit inside a proton or a heavy nucleus as a function of x and the resolution scale. You want to see exactly how the gluon density grows at small x, where saturation kicks in, and how that depends on whether you're hitting a single proton, a light nucleus, or a heavy one like gold or lead. You're not just asking, are there many gluons? You're trying to build a high-resolution 3D map in momentum space and impact parameter, a kind of CT scan of the gluon content. The tension here is sharp. We already know the broad outline, but the details matter. We don't yet know from first principles exactly how confinement emerges from the QCD equations. We don't have a clean, undisputed glue ball identified in the data. We see hints of gluon saturation and the color glass condensate, but we don't know how universal that picture is across different nuclei and energies. These are not small cleanup tasks. They sit right at the center of what is a proton and how does matter hold together. And this isn't just about particle physics in isolation. There's a cosmology angle built into all of this. In the early universe, when the temperature was above roughly 160 mega-electron volts, so around 1.5 trillion to 2 trillion Kelvin, everything was in a quark-gluon phase. There were no bound protons or neutrons. Gluons weren't a detail inside hadrons. They were one of the main degrees of freedom filling space. As the universe expanded, it cooled through that QCD transition. Quarks and gluons confined into hadrons. Those hadrons then participated in Big Bang nucleosynthesis, forming light nuclei like hydrogen, helium, and a bit of lithium. The exact timing and details of that confinement and cooling affect the density and distribution of matter, which in turn feeds into the structure we see later, including the pattern of the cosmic microwave background and the way galaxies and clusters form over millions of light years. Small differences in gluon dynamics at femtometer scales, at distances a billion times smaller than a millimeter, can translate into small differences in the equation of state of the early universe plasma. Those differences propagate forward into the way matter clumps on scales of kiloparsecs and megaparsecs, thousands to millions of light years. So when you measure something at the EIC or in heavy ion collisions, you're not just tightening a particle physics model, you're constraining the history of the universe in its first microseconds. Put all of this together, and the picture of the gluon you started with is gone. You might have expected the gluon to be the strong force version of the photon, a simple mediator that flies between charges, maybe with a few quirks. What you've actually met is a field that never appears alone because confinement blocks you every time you try. It creates most of a proton's mass and most of your mass purely as trapped energy in a self-interacting field. It ties quarks together with flux tubes that behave like strings, with a real tension measured in giga-electron volts per femtometer. It turns a proton into a completely different object depending on how hard you hit it, from 3 quarks at low energy to a saturated gluon sheet with quark impurities at extreme energy. It flows as a near-perfect liquid in quark-gluon plasma, and it forces us onto big supercomputers and four-dimensional lattices just to compute basic properties like hadron masses. And on top of that, it's still not fully nailed down. We don't yet have a clean analytic proof of confinement. We don't yet have an undisputed glueball. We're still mapping saturation. We're still refining the equation of state of QCD matter that filled the early universe. So this 1 degree of freedom, this one boson in the standard model chart, is responsible for holding nuclei together, setting most of your mass, shaping collider events, and influencing the first microseconds of cosmic history, while at the same time pushing our calculations to their limit. So when you hear particle and you picture a tiny billiard ball, that picture is already outdated. For gluons, particle is just the simplest label we slap on a mode of a field that is restless, self-interacting, and scale-dependent. Underneath that label, it's field dynamics all the way down, and this particular field refuses to behave in any way that matches your everyday intuition. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.